logarithms are one of the more difficult concepts in the pre-calculus curriculum. They're a difficult idea for several reasons. The first reason is the definition is difficult, and even then, once you kind of understand the meaning of logarithms, the process of calculating them is very challenging as well. So what I'm going to do to begin with is to define logarithms carefully and talk about how you can find them in certain circumstances. So let's remind ourselves how we started off thinking about exponents. So the first thing we thought about was if I took my basic operations, so addition and multiplication, and I repeatedly did them. So let's think about repeated addition for a second. So repeated addition is just the same as multiplication. So just as an example, if I was to take 3 and add it to itself 4 times, so 4 copies of this, we know this is equal to 4 times 3, basically by definition of multiplication pretty much. This is equal to 12. Okay, so what's the reverse process of this? Well, the reverse process is it's the reverse of multiplication, and the reverse of multiplication is division. So let's just kind of think about this. So the reverse process must be the inverse process to multiplication, which is division. Now, what do you mean by reverse process? Well, I think up here, let me explain what I mean. How do I go from 4 to 12? Right, that's kind of the forward process. Well, I would multiply 4 by 3 and I would get 12. So the reverse process would be doing this backwards essentially. So let's take a moment to think exactly what that means. So imagine I'm adding 3 to itself some number of times. So I don't know exactly how many, but let's label this as a times, where a is going to be some positive whole number, let's say. And let's imagine this is equal to 15. Okay, so the reverse of this is basically asking, well, how do I go backwards? How do I go from 15 to a? What's the procedure? So as I've just described, it's got to be division. Let's carefully check that. So this implies that 3 times a has to be equal to, or a times 3, it doesn't matter how you write it, is equal to 15. And then one of my basic laws of algebra says this implies that a is equal to 15 divided by 3, but that's of course equal to 5. And just to really be careful, what am I actually invoking here? I'm invoking the property that AB equals C implies that A is equal to, let's say, C divided by B. So this is the kind of a general property of algebra I'm using. Okay, this is kind of an if and only if condition, assuming B is non-zero. Got to be a little bit careful, otherwise things can go a bit wrong. And here B is 3, so it's non-zero. Very good. So I'm just being really careful about making sure every step is a very simple principle of algebra. All right, so that's addition, right? Repeated addition is multiplication. The reverse process is the reverse of multiplication, which is division, right? A familiar operation. What about if I repeat multiplication? So repeated multiplication is what I called exponentiation. So just as an example, let's say 2 times itself, I don't know, let's go to 6. So I multiply 2 by itself 6 times. 2 multiplied by itself 6 times. Well, that's equal to 2 to the 6, of course. That's the notation I'm used to using. What's that actually equal to? 2 to the 6 is 64. So let's kind of do an analogy with what's happening above. In a sense, what I'm doing is I'm going from 6 to 64 by raising 2 to the power 6, right? So the forward process, if you want, is this. Okay, so I go from 6 to 64 by raising 2 to that power. Very nice. Now, what's the reverse process? The reverse process would be going backwards. It would be essentially going from 64 back to 6. So this reverse process is the reverse of exponentiation, and that's not something we've encountered before. Previously, it was multiplication, so the reverse was definitely division. Well, you're very used to that. But the inverse of exponentiation is something new. So that's what logarithms are. They're the inverse process of exponentiation. So I will go through a few examples in a second, of course. Logarithms. So logarithms is exponentiation in reverse. So this is, in a sense, a new operation. And we're going to see it's a lot more complicated than division. It's more difficult, but it's something we're going to have to kind of get used to because it's going to be one of our core kind of new operations on functions, if you want. So let's do 2 examples, I think, just to make sure we understand what this reverse process actually means. So let's do exactly what we did really with the sum example, but we'll do it with multiplication. So 2 times 2 dot 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 some number of times. Let's say a times. Let's imagine this is equal to 32 for a second. So what does this mean? Well, this would imply that, well, 2 multiplied by itself a times, in my usual exponent notation, is 2 to the a has to be equal to 32. Okay, so what we're really trying to do here is the reverse of this exponentiation process. So we're trying, in a sense, to go backwards. So we're trying to work out what's in the opposite direction. So I'm looking for some a that does this. Now, thankfully, there is a pretty familiar a to us that does it. So observation. I mean, 2 to the 5 is equal to 32. That's true. So it turns out that's the only number that will work, right? There's the only exponent which will give me 32 if the base is 2. So there's one option, a has to be equal to 5. Okay. So that was okay, but it wasn't great because I needed to spot that 2 to the 5 is equal to 32. Let's do another example. So let's do 3 times itself a bunch of times. Let's do the same deal. Let's label this as a. And let's say this is equal to, I don't know, 81. So it's equal to 81. So what we're trying to do is the reverse process of exponentiation. We're trying to work out what a would do the job. Same story. So if this happened, we would have 3 to the power a is equal to 81. Does that look like anything we've seen before? Well, let's just go through some small numbers just to see what happens, shall we? So if I do 3 to the power 1, of course, that's 3. If I do 3 squared, that's equal to 9. If I do 3 cubed, that's equal to 27. If I do 3 to the 4, that's equal to, bingo, 81. So all of this tells me, essentially by trial and error more than anything else, I have a is equal to 4 is a solution. And it turns out that's the only possible, as we'll see in a moment. Right, so what I want is some notation here, right? I want to have some notation which talks about a being, in a sense, the opposite of exponentiation. So that's what logarithm notation is. So maybe I'll leave this up and just do it below. So notation. So to represent the relationship between the output here, 81 or 32, and the number of terms, the exponent, we use log notation. So the first guy, I would write log base 2, because 2 is the base, of 32 is equal to a, so a is equal to 5 here. So as with exponential functions, sorry, exponential exponents, the thing in the bottom is called the base, same thing for logarithms. And what about the second guy? Well, it would be the statement that log to the base 3 of 81 is equal to 4. So what are these shorthand for? They're basically shorthand for the following two statements. This is just alternate notation for the statement that 2 to the 5 is equal to 32. That's all it's saying. It's just funny notation for it. This is the same deal. This is just saying that 3 to the 4 is equal to 81. It's just new notation when it comes down to it. So, what should this notation mean in general? So essentially what we want to do is have a relationship between the base and the output, right? The exponentiation. So let's think about what the general case means. So the general case. So what have we got? Well, I've got some base, some power a is equal to c. And I imagine I know what b is and I know what c is, right? Just like here, I know 2 and 32 and 3 and 81. And I need to know what the exponent is. That's the a. So the notation I'm going to use for this is, so if and only if, the notation I'm going to use is log to the base b of c is equal to a. So that is going to be the meaning, if you want, of what log to the base b of c is. So this is very important. This is basically me defining what a logarithm means. If it plays nice. This is me defining what log notation means. So when you say log to the base b of c is a, it literally is the same thing as this. This is the meaning of the notation. So I always find this very confusing. Certainly when I first saw this, it's like, oh my goodness, this is so confusing. It's all backwards. I'm not used to exponentiation done backwards. But this is a definition, so let me kind of write this here. So again, as I've said previously, definition means this is the meaning of the notation. Right? There's nowhere, we can't go any further back than this. This is it, right? Now I do want to say a few things about this. First of all, we don't want b to be negative, because if b is negative, we have terrible problems with powers. So let's just completely ignore this issue. We don't want to define any logarithms or anything like that when b is negative. So we'll assume b is greater than 0. Next, we don't want b to be equal to 1. The reason for that is if b is equal to 1, I mean 1 to any power is just 1, so this would be very meaningless when it comes down to it, right? So we don't want to include 1. That doesn't make sense, okay? Basically 1 to any power is equal to 1 for all a. Okay, so for the meaning of log, you need to, at the very least, b has to be strictly positive and it can't be equal to 1. Next, a little bit more notation. Here. Often people drop the base, and if you drop the base and just write log, what that means is log to the base 10. Now the reason that's natural is because log to the base 10, it deals with base 10, and 10 is one of the most commonly used bases. Remember, decimals are all in base 10, so it makes sense that this is somehow privileged. You'll find out when you go on to do calculus, there are other bases which are in many ways more important than base 10, but for the moment, it's worth thinking about them in general. A few special cases as well, just to make sure that we really understand this. I mean, we'll talk about intuition for calculating these in a second, but really simple cases are the following. Well, b to the 1 is equal to b, right? Of course. So that implies what? It implies that log to the base b of b is equal to 1 by definition, right? Similarly, b to the 0 is equal to 1. So that would imply log to the base b of 1 is equal to 0. Okay, so these are just coming from the definition if you want. So really what I want to say about this is a little bit about calculation first of all. So there's an intuition that goes into this. This is a very confusing statement. It's like, oh my goodness, what am I meant to do here to calculate this? Here's how I think about it. The intuition is, I mean, what do we need to raise b to in order to get c? That's kind of the question I ask myself. To raise b2 in order to get c. That's kind of the thing hardwired into my head. I say, okay, what power of b do I need in order to get c? Now, we know powers can be anything now if I'm assuming b is positive. Remember, b to the a makes sense for any number at all. So there's no reason the output of a logarithm has to be a positive number. So let's do a couple of examples. A couple of examples. First, let's do log to the base 9 of 3. So what's this equal to? So what do we need? So we need an a such that 9 to the power a, so let me write that more carefully, such that 9 to the power a is equal to 3. Well, what works? Thankfully, I know the square root of 9 is equal to 3, so 9 to the power a half is equal to 3. So this will imply, well, this actually guarantees that log to the base 9 of 3 would have to be equal to what? It would have to be equal to a half. That's actually the only number that's going to work, as we're going to see in a second. So the logarithm doesn't have to be a whole number. So that's the first thorny issue. Let's do another one side beside it to illustrate another issue. What about, let's say, log to the base 4 of a quarter? What does that mean? Well, again, we need to find an a such that, okay, what's it going to be? It's going to be 4 to the power a has to be equal to a quarter. Thankfully, this is a very obvious example, right? This is my standard reciprocal. 4 to the minus 1 is equal to 1 over 4. So what does that tell you? It's going to tell you that log to the base 4 of a quarter is going to be minus 1. So interesting, the output of a logarithm could be negative. And that's pretty obvious, really, because this thing here can be any positive, well, it can be any number at all, positive or negative, right? As long as b is strictly greater than 0. Okay, so interesting. So these examples were only really doable by hand because we could spot a power that worked. The problem is we can't do that in general. And this really is what makes logarithms so difficult on a first sweep. So problem, at least for calculating things, it could be very hard. It could be very hard to find exact value by hand. So I'll give you a little bit of intuition here. Imagine if I asked us, I don't know, let's do log to the base 2 of 40. And I asked us, what's that equal to? So I'm going to sit down and just try to work out powers of 2 and see what could be going on. So 2 to the 1 is equal to 2, of course. 2 to the 2 is equal to 4. 2 to the 3 is equal to 8. 2 to the 4 is equal to 16, getting bigger. 2 to the 5 is equal to 32. Okay, not far off 40, but then unfortunately 2 to the 6 jumps all the way up to 64. So intuitively, this is not precise mathematics, it seems to me that the a I'm looking for is going to be somewhere between 5 and 6, because as I move from 5 to 6, the exponent is going to move from 32 to 64, and at some point it's going to hit 40. So that's not precise, but it is correct logic, it turns out. So there is some number between let's say 5 and 6. So some number, I'll just say some a, such that 2 to the a is equal to 40. And that's what we're looking for. That would be the logarithm. But it's difficult to get your hands on. So you can see, first of all, logarithms are not easy to understand, difficult to calculate, and also there are certain circumstances where they don't really make any sense. So let me talk a little bit in general about what logarithms look like and when they exist. So here's some important facts. Important facts. So again, we're going to assume b is strictly greater than 0 and is not equal to 1. Otherwise, it doesn't really work. Okay, so let's think about log sub b of c. Now, does this make sense? For it to make sense, you'd need to be able to write down c in the form 2 to the power a. Now, it turns out that can be always done if c is greater than 0. Right? Remember, c is equal to b to the a in theory. Turns out you can always do it. So we can always find actually a unique a. There's only one number that does it. I've already kind of alluded to this a little bit. The unique a such that b to the a is equal to c. So this tells you, great, the logarithm makes sense. There's only one choice for the logarithm, all good, right? So the log BC is defined. Of course, it's equal to a. There's only one choice. Fantastic. For example, I don't know, 2 to the power of something is equal to 4. Well, the something in the exponent has to be 2. There's no other option. But if it was 2 to the power of something was equal to 1,000, there'll also be some number. It won't be easy to get your hands on it, but it'll be there somewhere. And that would work with smaller numbers too, as long as they're positive. For example, 2 to the power of 2 to the power of something equals 1/2. That something would be -1, like we saw a second ago. 2 to the power of something is equal to 1/4. That would be -2. So this a could be negative, and the more negative it is, the smaller the value of c, if you want. Okay, what about if c is negative? Or indeed equal to 0? Well, then it's no good, right? Remember, one of my properties of exponentials was the fact that if b is positive, b to any power is always strictly positive. So b to the a is always greater than 0. Strictly greater than 0 for all numbers a. So this implies b to the a can never equal c, ever. So that means no a will work. So that tells me log sub b of c is undefined. It's undefined, doesn't make sense. So the takeaway is if c is strictly greater than 0, there's a logarithm, there's only one. If c is less than or equal to 0, it doesn't make sense. So just as a quick example here. So example, if we had a scenario with c is -1, so 3 to the x, let's say the base is 3, that has no solutions, right? 3 to any power is always positive. I'm only using x here because we're just used to solving for x, but it has no solutions. So this tells you that log to the base 3 of -1 is undefined. Doesn't make sense. So it's kind of quite subtle general properties. So the last thing I want to do is to talk about an important simplifying principle when you're dealing with logarithms or exponents. Actually, maybe I should write a conclusion down for all of this. So let's just write this as a conclusion. I think that might be a good idea. So the conclusion of what I just said basically is the following. Log sub b of c is defined if and only if c is greater than 0. And again, when I'm writing this down, I'm always assuming that b is not 1 and it's strictly greater than 0. So b has to be bigger than 0 and b is not equal to 1. Can't be 1 because 1 to any power is just 1. So that's kind of the conclusion of what I've just said in this more complicated diagram. So finally, a very important property which will allow us to manipulate equations with exponents and logarithms is the cancellation property. So we'll get a lot more practice with this in further videos. So cancellation properties. So these are true basically by definition of log, but it's worth writing them down. If I take b and I raise it to the power log b of c, this is just equal to c again. Okay, of course, that's the definition of log. So maybe if I move this down for more space. And we could also take log of kind of an exponential. Log sub b of b to the a is just equal to a, basically by definition. So these are the cancellation properties. They allow us to, in a sense, cancel logarithms with the first if I raise them to a power, and cancel an exponential or an exponent if I take log of it. So we'll get more practice with these in further videos, as I said. Worth saying here, of course, c has to be greater than 0, b has to be greater than 0 and not equal to 1, and a can be anything. Remember, you can take b to any power if b is positive. So these are the cancellation properties. Let's do a quick example, a numerical example. I'm not going to go into complicated examples yet. But let's just make sure it's true, shall we? So 3 to the power 3 is equal to 27. So this tells you what? It tells you that log sub 3 of 27 is equal to 3. Okay, so let's just check both sides and show they're equal to each other. So this implies that 3 to the power log 3 27 is equal to 3 to the power 3, which is equal to 27, tick. That is the first property, exactly the same. And of course, the second one is kind of totally obvious. Log, but it's not obvious, but it's just true by definition. Log the base 3 of 3 to the 3 is just 3. Or maybe I should just say, to really hammer it home, this is log to the base 3 of 27. And as before, we've seen that's equal to 3. So these are both true. So to recap, logarithms are essentially the inverse of an exponentiation. So this is the crucial defining property of logarithms. They're difficult to calculate. In general, you can't really do it by hand, and their existence is a little bit delicate. It all depends on your b and your c. We always assume b is strictly greater than 0 and b is not equal to 1. That's part of the assumptions the whole time, but you can't take log of a negative number because b to any power if b is positive is always positive. Whereas a logarithm can take any value as an output if you want. A can be anything at all. So this value can be anything because we can raise b to any power we want. Negatives, positives, whatever. So that's what logarithms are. Next time we'll look at laws of logarithms.